Can people on Zoom hear me? Hello. Can anyone hear me on Zoom? Test, test. Chat's on now. All right. All right. Good afternoon. How's everyone doing? All right. Uh, Only a few things left in the class. Uh, Homework 4 we are going to release soon, it seems. It's going to be due the Sunday before our week. Other than that, Project 3B is getting close to its due date. How's everyone doing on that? Doing well? Uh, this is around the time when it's going to start to become really difficult to like add new things to your project. Because you've been working on it really quickly. It's difficult to like add things while making it robust. Uh, just out of curiosity, how many people are getting into that kind of phase? They are like starting to build new things, they're adding new things, and then it's just harder to add things now that you've been building stuff. Anyone coming to that? Yeah. Anyone have any cool features that they've built already so far? Built slash building. Yeah, I'm curious to hear what y'all are doing. Huh? Ah, Bomberman. Yes. Someone's building Bomberman. Anyone else? Any ideas that you're all building right now? Kind of curious to hear what y'all are making. No one else? There should be some fun, cool mechanics. Your games are more cool than you think, I think. Anyway, let's get started with today's lecture. So, so far, we've covered a few sorting algorithms. We've covered heap sort, insertion sort, merge sort, quick sort. Uh, in effect, here's kind of a quick rundown of how they work. Selection sort, we just find the smallest item, we put it at the front. Insertion sort, we move each item one at a time into its right spot. Merge sort, you split the list in half, you sort each one individually, and you kind of merge them together to form a single sorted list. Quick sort, you take an item, you put it in the middle, you split it into items smaller than that, items bigger than that, split recursively sort those sides, and then you have a fully sorted list. We saw that when we do experiments, heap sort, merge sort, quick sort, even though all of them have theoretical and log n behavior, quick sort ended up being the fastest. Heap sort was really slow. We didn't show you this, but heap sort is actually really slow. Merge sort is kind of in the middle there, and then quick sort is effectively the fastest one in general. Now, there are other things that you might use for sorts, right? Some students were asking, why do we even teach heap sort, merge sort when quick sort is already the fastest? Well, that's because depending on the sorting algorithm you use, you might have different properties. One of the properties we might be looking for is stability. So a sort is stable if the order of equivalent items get preserved. So if you see in this list here, we have 4 people who have a 3 associated with them. So you might imagine that these are students along with their year. There's 3 students right now or 4 students right now who are juniors. And if we sort this and we want a stable sort, then we're going to end up getting those items in that same order. So right now, this is sorted by their name. At the end here, we have the list of juniors sorted by their name as well. So this is a stable sort. Here's an example of a sort that isn't stable. You can see here that all the items that were juniors, they end up getting like mixed up randomly. Uh, Generally speaking, we do actually like stability. Instability in sorting can be rather annoying. Let's say that, for example, I'm trying to look up a list of all of my students, right? Uh, I might first want to sort them alphabetically and then by their year. So that way I get all the juniors in my class sorted by their name alphabetically. If I have a stable sort, then I can do that. First I sort by name, then I sort by section. If I don't have that ability, if I don't have stability, then I can't do this easily. I need to split this list into a piece that contains only the juniors, sort that separately, split the list into a part that contains only the seniors, split that separately. It's more annoying and it takes a longer time to run. So let me ask a quick question. Is insertion sort stable? Let's take a minute or so to discuss this. And also same thing with quicksort. Is quicksort stable as well? All right, let's bring everyone back. What do people say? Is insertion sort stable? How many people say yes, it's stable? How many people say no, it's not stable? How many people say something else, like it depends? Or how many people didn't say anything? All right. The sum total of people who said yes, no, and didn't say anything is about 2/3 of the class. So 1/3 of the people are in a I don't want to raise my hand mode. All right, sorry. Anyway, so can someone explain why insertion sort is stable? Yeah, you.
Because if you get to a case where you have two identical things next to each other, you won't swap them. So there's no possible way that once you toggle together will work.
Yeah, because insertion sort only moves things one at a time, we just need to see if at any point two equivalent items get swapped. And this never happens because when we compare two items and we see that they're the same, we don't swap them over, at least in this version of insertion sort. How about quicksort? Is it stable? How many people think quicksort is stable? How many people think it's not stable? How many people think it depends on the exact version of quicksort we're working with? All right. So for the people who said it's not stable, why do you say it's not stable? Yeah. Yeah. So if we are using for partitioning, it's definitely true that if we swap two items only when they're greater than or less than, according to these pointers, then you can end up in a position where items swap orders. Once you have two items that are the equivalent value and they end up swapping, it's very hard to undo that in the next step. So generally speaking, once you get to that point where you're swapping items that are the exact same value, you end up coming to an unstable sort. Any other points? There were some people who said it depends. Is there any version of quicksort where it doesn't or where it is stable? Yeah. Yeah, if you do a three-way partitioning, then you do still end up with a stable sorting algorithm because you are keeping everything in the same order. Now, we never use three-way partitioning because that is way slower than even merge sort. But it is a way to make quicksort stable. I will say that generally speaking, we don't have a stable version of quicksort that's fast. Especially one of the easiest reasons why is because when we start a quicksort, we generally like to shuffle our list at the start. And if we shuffle our list, then we lose all the information about which items were ahead or behind it at the start of the algorithm. So insertion sort, it is always going to be stable, at least with the versions that we teach you, right? We always say that if you have equal items, you don't move them. So insertion sort will be stable. Quicksort, it won't be stable in certain partitioning schemes, in certain setups to avoid the worst case behavior. Generally speaking, the only way you can get a stable quicksort is if you use three-way partitioning and you don't include some shuffling algorithm at the start. And generally speaking, that means that you just have a really slow quicksort. So you're not going to be doing that anyway. So if you look at the exact behaviors, you can prove the other things by yourself at a later time. But you'll see that insertion sort and merge sort are stable algorithms. Heap sort, the version where we use a max heap, that's not going to be stable. And quick sort, at the very least, the version that we use with shuffling and then using for partitioning, that is not going to be stable. Other than that, you do see the memory use. Heap sort, insertion sort are both theta 1 because they're doing things in place. Merge sort, you need that auxiliary array. So that takes theta n memory. And quick sort, it does use log n memory. Even if you do it in place with something like for partitioning, you still need that in order to deal with the call stack. If you have log n maximum recursive calls, then you'll have log n size call stack, 1 unit of memory for each function call, recursive call down the line. Now, if you look at how Java actually behaves, it does something really interesting. It uses merge sort, or a tib sort version of merge sort, which is slightly it's a slight variant of merge sort. If the array consists of objects. But it uses quicksort if the array consists of primitives. Why do you think that is? Does anyone have any ideas of why this might be the case? Yeah?
uh, they can't really be distinguished in any way. Like they're singular types. These objects, like they're gonna have, if you want to make sure that it's stable, like it's still gonna maintain that.
Yeah, that's a good reasoning. Objects, they might have specific values that mean that stability is important, right? Two things might be considered equal by comparison and still be different. And you want to have stability. Stability is a useful trait to have. Quicksort isn't stable, but if you're having lists of primitives, then two things are equal in terms of the comparison, if and only if they're exactly the same numeric values. So because of that, there isn't really a need for stability. This copy of 5 is the exact same as this copy of 5. But this dog might be different from this dog, even if they have the same name. So because of this, quicksort is more efficient. It's faster to use. You are going to want to use that for primitives. But merge sort or a stable sorting algorithm might be used instead if you have a list of objects. So because of this, you do end up needing these two different types of sorting algorithms. It's interesting to see how Java like picks the right sorting algorithm depending on the problem. If you know that there is really only one way that equality is only defined if two things are exactly identical as numbers, is there a way to force Java to use quicksort? Well, what do you think? Does anyone have any way that they might do that? Yeah.
I can make an object that just stores things, use quicksort or use sorting on that object, and then turn it back into the input.
Uh, yeah, if there's a way to convert the object into an integer somehow, yeah, you could convert everything into integer, sort the list of integers, convert everything back. That could work. Yeah, of course, you do need to find a way to convert things into integers that matches the comparison. That's not necessarily possible. Yeah, but that is a generally good way to do things. Yeah. Now, there are a few other things that you can do to optimize your sorting algorithms. You can switch to insertion sort for small sizes, right? Insertion sort is generally going to be the fastest for really small lists because it's much faster when dealing with items that have a lot of already existing order to them. It doesn't compare as many things, so it gets to the root of the sorting problem faster. You can also use adaptive sorts. Insertion sort is an example of an adaptive sort. Tim sort is actually adaptive. It takes advantage of pre-existing order in the list. I think if I remember correctly, what it does is it first looks for runs of consecutive data that's already in sorted order, and it uses that as a start for your merge sort. So if you have a lot of items that are already in the right sorted order, then it doesn't need to go all the way down to the recursive like small sizes for merge sort. You can also use some information about the keys. If you know the keys are a certain set of values, then you can sort things in a faster time. And then for quicksort, if the algorithm can check to see how deep its recursive call stack goes and switch to a different sorting method, that might be a better approach. Now, this is only really a problem for deterministic versions of quicksort. If you have a randomized shuffling at the start, then generally speaking, you don't have to worry about you accidentally shuffling things back into sorted order. If you are going to worry about quicksort accidentally shuffling your items back into sorted order, then you should be worried more about cosmic bits, cosmic rays hitting your computer and flipping bits, which does happen on occasion. Yeah, it's actually no laughing matter. Once you get into like space, for example, computers, you actually need like 3 different computers running at the same time, computing the exact same thing, because you're not sure that any one of them is going to actually yield the right result. There's a chance that a bit gets flipped by a cosmic ray. But anyway, if you're not worried about cosmic bit flipping, you're not worried about quicksort yielding a random result. Now, today we're going to be covering 2 different sorting ideas. The first one is addition by digit sorting. The second one is counting sort, and we'll build up to a new sorting algorithm called Radix sort. Now, the reason why is because like we've already concluded that like there are certain like sorting algorithms that doesn't work. The ultimate comparison sort we already proved was n log n. Once we get these items solved, we'll be able to sort numbers in theta n time with some small asterisks, but we'll get to that. So let's start off with the warm-up. Let's say that we have a list of integers, and we sort only by the rightmost digit. So just as a quick exercise, what are going to be the last four items in this list here? We're sorting only by the last four digits, or by the last rightmost digit. What are the items going to be? For reference, the items that are colored on the left side are the only items that are left over that haven't been moved in. So everyone shout it out. What's the first item? 53. Second item? 23. 34. 34. Is that the only possibility? No? What's the other possibility? Yeah, it's possible that 23 and 53 might have swapped. In this case, I put 53 and 23 order. It might be in a different order, depending on if the sort I use is stable. If I have a stable sort, then 53 is always going to come before the 23. If I have an unstable sort, there's a 50-50 chance that the 23 is going to come first. Now, let's say that I've sorted first by this rightmost digit, and then I sort by the leftmost digit using another stable sort. Here I've already moved over the items with first digit 1, 2, and 4. Let's say that I want to move in the items with threes. What are the items going to be in order? Everyone say it aloud. 31, 32, 34, 34. Yep. Anyone notice anything about that last list? Well, we use a stable sort, yes. Uh, Anyone notice anything about the order of the items on the right side? Yeah, they're in sorted order. How'd that happen? We just sorted by digits randomly, and now all of a sudden we're in a fully sorted order. Does this always happen? Well, as it turns out, it does. Can anyone give a reason why this will always happen? Yeah.
So every digit is being sorted by from the least important digit to the most important. So by the have even if the rightmost column is not necessarily sorted, by the end you'll get sorted list because the
Yeah. In a way, this first pass of the sorting algorithm, what it did was it moved all the items with last digit 1 at the start, after all or before all the items with last digit 2, before all the items with last digit 3, and before all the items with last digit 4. When we move to the next digit, those items kept in their relative position. So that means everything that's like 11 comes before everything that's 12, then 13, then 14, then 15, and so on, because they all have the same first digit, and their second digit, they stayed in that order. And then if we kept doing this over and over, then eventually we end up with the topmost digit being in sorted order. Everything within the topmost digit, if they're the same topmost digit, then everything's in order from there, and so on and so forth. And that's effectively the definition of fully sorting a list. Now, this only really works if this sorting algorithm is stable. If it was unstable, then you might get something like this. And now you don't have a fully sorted list. But if you use a stable sort, move from least digit to most significant digit, then you are going to guarantee ending up at a fully sorted list by the end of it. Anyone have any questions on here? I know this is kind of like a bit of a logical leap. It's a bit tricky to see why this is true. I definitely recommend trying out a few examples on your own when you have the time. Any questions? Yeah.
I guess like if you have a really long digit, for a really long number with many digits in them, it gets to a point where you're technically using like n squared work instead of like n work because the digits are just.
If you get to a really long list of digits, does it potentially lead to n squared? No, but that's because n isn't necessarily the length of the numbers. We'll come to that idea in a bit. Keep that in mind. There are some difficulties with using this for certain types of data that you're kind of hinting on. But right now, if we're dealing with numbers and the numbers have a relatively small number of digits, then this is going to work really nicely. Yeah.
What if the number of digits for each of the entries is not the same?
What if we have different numbers of digits for each entry? Good question. What will you do? What do you think we can do if different numbers have different numbers of digits? Yeah.
And look at like the ones that have like the same number of digits, like some are like greater, like those would be before the ones that you would have sort of that have less digits.
Only look at the ones who have the same number of digits. Well, if you do that, you're going to end up, I think, putting all the one-digit numbers first before all the two-digit numbers. Does that? I guess that depends. Yeah. Yeah. The other way is to just treat lack of digit as the same as a zero. If you do that, then you just end up making sure that everything has the same number of digits. And that is numerically what we mean, right? 1 is the same as 0, 1 is the same as 0, 0, 1, and so on. Now, there's a few quick notes right now. Right now, we don't have a really obvious reason why this procedure is useful. We could have just sorted the entire integer instead of sorting it 3 times. But we'll look at how we can sort digit by digit using a faster runtime approach. We'll come back to this in a bit. For now, let me talk about another sorting algorithm. So comparison-based sorting, it is going to take at least n log n time. We've proven from last time that if you use comparisons to sort a list, then you are guaranteed to have omega n log n runtime worst case. It could be worse. Insertion sort is a comparison sort that takes n squared time, but we are never going to find something that's better than n log n in the worst case. We can actually go even further and say that it's not going to have n log n in expected case, right? We saw quicksort, for example, as n squared worst time behavior, but n log n average case. You can show that you're never going to get better than n log n average case in this, but the math is a bit more tricky to prove that. Either way, the ultimate comparison sort is going to have a worst case runtime of n log n, which means that no matter how clever we are, no matter what you're trying to come up with, you could spend a million years trying to solve this problem. You're not going to find a better sorting algorithm, at least theoretically, than merge sort or quicksort's expected case. Unless you don't use comparisons. All of this relies on the assumption that we're using comparisons. If we have more information about the data, we may not necessarily need to use compares at all. We might be able to solve this problem without comparisons. So here's an example of a sorting algorithm that doesn't use comparisons. It's not particularly good. It's called sleep sort. The way that it works is that for each integer x in the array, you start a new program that sleeps for x seconds, prints x, and we all start them at the same time. In effect, imagine that you have a bunch of timers, right? So if you want to sort the list 30, 50, and 20, you set a timer for 30 seconds, you set a timer for 50 seconds, you set a timer for 20 seconds, and you wait. Ding, 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 you write 20. Ding, 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 you write 30. Ding, 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 you write 50. Does this sort the list? Is this guaranteed to sort the list in correct order? Yes.
I think it would depend a bit on your insert. If you're just printing out, it would. But if, for example, if you had elements that were the same value, I could imagine, depending on how you're inserting it, if you're inserting two elements at the same time, it would help try to
you are getting into really clever territory. If you have two items that are the exact same number, then you might run into like conflicts, right? If two different programs try to write at the same time to the console, what happens? You'll talk about this more in actually 162. But there is a way to prevent this. In effect, the console gets reserved by each program. So it basically just waits in line to write down its data. So it's going to guarantee that it's not going to like cause that issue.
Kind of like a waiting list or cache or something.
Yeah, it's kind of a waiting list. What it's actually called is a lock, um, or a mutex. So you just lock the console, you take control of the console for a brief second, you write whatever you do, and then you leave, right? Yeah, I like to think of it like a bathroom stall lock, right? You make sure that people wait in line instead of letting anyone just barge in and go in. Now, what is its runtime? If you have n numbers, let's say the largest item is A as a value. What's the runtime for this? Anyone have a, yeah, n plus A? Why do you say that?
Then, once you start the program at the same time, it's gonna take at most 8 seconds between all of them.
Yep, n plus the largest value in the array. Yeah, because you need to go through all the items to set up all these programs. That takes n units of time. And then the array A, the largest item is going to be however long the sleep is. Uh, it was invented by 4chan, by the way, at least in theory. Now, I will point out that there is actually kind of a bit of a catch, because a computer is actually only able to run one program at a time. And what it actually is doing is it's swapping between programs really, really quickly. And the way it does that internally is it sorts the list of programs by what point they're next going to start running, which means that you've effectively reduced sorting back into sorting again. Only this time it's the operating system that's doing the sorting, so you didn't need to write any code. But in any case, this kind of shows that in some worlds you can create sorting algorithms that aren't comparison sorts, but which run in time faster than n log n. This is theta n time if your a's are really small. So let me take a look at another example of a sorting algorithm. Let's say that you, for some reason, already know that all the keys are unique. All the numbers that you're sorting are all unique values. And they're all unique values from 0 to the maximum size of the array. So in this case here, we have the number 0 up to 11. Each one is shown exactly once. Can you sort this more efficiently than using a regular sorting algorithm? Yeah.
If you're okay with like having padding between them, could you just put all of them in like a big like a hash map or like a set like thing or some hashing thing? Like you'll have a bunch of
Well,
padding.
you don't even need padding because I've said that every single number is here. Every number from 0 to 11 is here. And each number is here exactly once.
Oh, okay. So just make an array with the number of unique outs. Assign each one to an ID, create an array with size of all the unique IDs.
Yeah. So if you look here, right, we can move this 5. We know that it's going to go into index 5 because we have one unique item for every single one. So we put it in the 5 spot. Where does the 0 spot go? Index 0, the front of the list. Where does the 11 go? Index 11. Where does the 9 go? Index 22? 9. Index 9, yes. And then so on and so forth. We sort this list fully. Does this work? Does this guarantee working behavior? Yes. How much time did it take? Theta n, yes. O of n, theta n, same thing, but yeah. Yeah, this runs in theta n time. Effectively, we just avoided all of the problems of sorting using comparison sorts. We are able to get it in theta n time. Now, the unfortunate thing is, does this work in general? No. We can guarantee that you're going to not have anything that works in general. Because if you want a generalized sorting algorithm, then you do need to rely on comparisons only. And that gets us back into the puppy cat dog problem of n log n. But if you knew for a fact that all of your numbers were between 0 and 11, and they were all unique values, then you could sort it this way. Now, there are a few more complex cases. If you have non-unique keys, non-consecutive keys, non-numerical keys, you're going to have some issues. Let's take a look at how to solve some of these problems. So let me start with this. Let's say that instead I am giving card suits to each person, and I'm going to order them according to this order: clubs, spades, hearts, diamonds. Uh, this isn't a common sorting order for the suits, but it's a fine sorting order. Let's say that I want to sort this, and I'm going to ask you this: what is the index of the first heart going to be? Can you tell without fully sorting the list? How can you tell? Let's take a minute or so to come up with that.
As it goes,
All right, let's bring everyone back. What do people say? What is the position of the first heart? Yeah. Index 5? How many people agree that it's index 5? Anyone have a different answer? All right. Yep, it is going to indeed be index 5. The way you can figure that out is you just look at how many clubs and spades there are. There are 3 clubs to start with. So they're going to take the first 3 spots. Then there's 2 spades. Those are going to take the next 2 spots, which means that the first heart ends up being put after all 5 of those items. So you're going to end up getting it at index 5. Now, this brings us to an interesting way to sort the list. We're going to call this counting sort. The way that we're going to do this is we're going to count out how many of each item exist. We're going to iterate through the list using the count array to decide where to put everything. Here's kind of how it's going to work in practice. So first off, I'm going to count out the number of items of each type. How can you do this? Any simple ways to do this? How do I get from this list down to the number of counts? Yeah, in the back. Yeah, some kind of hash map associating suits with numbers and then adding them up. You probably want to eventually convert this into an array so that because you want to have an order of the alphabet. But yeah, this can be done theta n time. Yeah, this sounds like theta n time algorithm. Once you know the counts, you can determine where the starting points are for each item, right? So all the clubs, they're going to start at position 0. The spades are going to start after all 3 clubs, so that's position 3. The hearts are going to start in position 5, which is after the 3 clubs and the 2 spades. The diamonds are going to start in position 9 after the 5 black cards and then the 4 hearts. Once we have that, what we can just do is look through each item and put it in the right spot. So Lauren is a spades. Where does she go? Everyone? Position 3. Yes, position 3, because 3 is a starting point for the spades. So what we'll do is we'll move this in, and we'll update the position of spades to be position 4 now, because that's where the next spade will go. Where does hearts go? Position 5. So we update the 5 to a 6. Where does the diamond go? 9, because that's a new spot. What next? Where does the next item go? 0. And then? I'm hearing 5, 6, and 4. Which one is it? Position 4. Because position 4 is the spot for the next spade. What next? Well, we're moving Sandra next. Sandra's a diamond. 10. And then? Swimp goes where? 6. James goes 7. Lee goes 1. Dave goes 8. Behrman goes 2. Lisa goes 11. And now, using this, we have fully sorted our list. How much time did that take? Theta n. Yes. Do you have a question?
How is like normal sorting algorithm? Like, there's no way to categorize them in like four, like you can have right?
Good question. Does this work for general data sets? It really depends. This only really works if the set of numbers that you're dealing with, or the set of like values you're working with, are only in a fixed small set of data, right? In this particular case, there were only 4 possible keys that we needed to sort by. So that's what made this more efficient. Let's actually take a look at the runtime specifically. Let's say that we have a list of 100 cities by population. What would be the expected worst case runtime? Which one do you think is going to be better, counting sort or quick sort? Counting sort, we have a list containing every single possible value to start with. Quick sort, we start off with, we just do the quick sort as. Which one do you think is going to take longer? How many people say counting sort is going to take longer? How many people say quick sort is going to take longer? Seems, yeah. How many, it feels like we're kind of in the middle. Does anyone want to give an argument as to why counting sort is going to take a longer time? Anyone? Anyone want to give a reason as to why quick sort would take longer? Yeah.
Well, I guess the sort will take longer because there are too many categories.
Yeah, counting sort is going to take longer because there's so many categories. Yeah, that's a good argument, right? Like, what's the largest city's population, do you think? Yeah, in the world. 1 billion people. I do not think there are 1 billion people in the largest city right now. That would be 1/8 of the world's population. But probably somewhere in the million-ish, right? I'm sure there's some really big cities in probably China has a lot of big cities. Beijing's probably really big. Yeah.
Despite that, there's only 10 things in our alphabet.
There's only 10 things in our alphabet? Well, with counting sort, this version of counting sort specifically, there's actually more things in our alphabet. There's a number 1 in our alphabet, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Every single number is a distinct value. Yeah. You're getting ahead of yourself. Yeah. Apparently, the largest city in the world at the time when this slide was first written was Tokyo, with a population of 37 million and change, which means that we are going to need an array of up to 37 million items. And most of these are just ones. Is this good? No. So if you have counting sort with a list of n total keys, and your alphabet is size r, so there's r different values that you could possibly be, what's the total runtime? N plus r, yes. This is specifically if we treat R as a variable, not as a constant. And this is relevant because we do need to make sure that our alphabet is small when dealing with counting sort. You only really get theta at runtime if your alphabet is small. So the total runtime, if you have n keys and an alphabet size R, is theta n plus R, because you need theta R time to fill out the counting array, and you need theta n time to just move everything into the right spots. The memory usage is also theta n plus R, because you need space for both the new array and for the counting array. But as long as n is significantly greater than R, you should expect reasonable performance. Now, n greater than R means that you are going to get repeats a lot. This is kind of why this doesn't get used in the puppy cat dog problem, because in the puppy cat dog problem, we assume that every single item was unique. And because every single item is unique, n must be exactly equal to R. Or at least less than or equal to, if R includes other items that could exist. So let's give some examples. Give some examples about when when counting sort is going to be clearly faster than quicksort. We already saw that counting sort can be potentially much worse than quicksort if the numbers are really big and there's only a few items. When might counting sort be better? Anyone have an idea? Just yeah. Huh? Yeah, let's imagine that you have just a bunch of dice rolls, like a million dice that you roll, and you want to sort their order. You're only going to get 6 distinct numbers. In that case, R is significantly smaller than the value of n, so you are going to get theta n time instead of n log n. Any other cases? Yeah. Flipping a coin. Yeah, anything that just kind of limits the possible values to be only a small data set. I,
This is a bad example, but if you're willing to accept some degree of error, like for example, when you're ranking cities, maybe you don't really care if like New York is like 1,000 people than Chicago or not. You just want like if you're willing to quantize the number of population millions. So
interesting. If you take your data set, then round it to the nearest, let's say, 1,000 or so. Then now you have a smaller list of values, and then you can sort it efficiently with counting sort. That's a clever idea, and it does actually work. We are actually going to talk about this. This is effectively equivalent to one of the versions of Radix we'll be talking about in a bit. So counting sort overall, it works because you have a small list of possible values. It's nice, but because its alphabet is limited, we are going to run into issues. So what can we do? We've come up with 2 different approaches today. What happens if we combine these 2? Let's take a look at this. Counting sort works when the alphabet is small. And digit by digit sort really works if you have a sorting algorithm that really works nicely when you're sorting by digits. How many distinct digits exist? 10? Is 10 small? Yeah, 10 small. So here's the idea for radix sort. We use counting sort as a step in our digit by digit sort. So here's an example, right? Here's how our digit by digit sort works. If we can use counting sort as this intermediate step, then this is going to work nicely. Now, in order for this to work, we do need it to be stable. Is counting sort stable? Yeah, counting sort is stable. So that means we can get this to work. Because we're only looking at a single digit, counting sort is efficient because you only have 10 digits to work with. And because you're using digit by digit sort, you only need a certain number of passes, the number of passes corresponding to how many digits there are. This is an LSD sort. What do you think the runtime is for this? Anyone have a statement? Just theta n? Why? Huh? Well, n with an asterisk. Sorry, this is the point where you get the asterisk. Yeah.
Theta n plus 20.
N plus 20. Well, that's true if we're dealing with 2 digits. And the 20 might change depending on well, the 20 is also like not relevant because it's a smaller order term. But you're getting there. The sorting algorithm, each time you run a counting sort is going to take n plus 10 time, which is theta n. How many times do you need to do a counting sort? Twice in this case because we had 2 digits. What in general? We don't know. It's not dependent on, and it's actually dependent on the values, right? So if we say that each item has at most W digits, it is going to take Wn plus WR time. It takes W times N plus R, where N plus R is the time for counting sort. Now, there's a lot of like variables in here. In practice, most of these variables are going to be constants. The size of the alphabet, for example, that's going to be always 10 for numbers. We might actually pick a smaller number like 2 because computers like working in binary. But R is going to be a constant in general. W, the number of digits in each item. Generally speaking, for integers, we can say that they're generally going to be constant as well, because Java limits the size of numbers to like a billion or so. That's only like 9 digits max. So let's just look through how things might work for other cases. If you have non-equal key lengths like this, how does LSD sort work? We already discussed this earlier. We just add zeros to the front, right? And once we do this, we can get it sorted. So using this LSD sort, we can get Wn plus WR runtime. In practice, W is probably going to be a small number, R is probably going to be a small number. So all you're left with is N, and you're left with theta N runtime. That's why I said with a bunch of asterisks. Now, there's a bunch of other versions of Radix sort. The other version we'll talk about is the most significant digit version. This version, instead of like sorting from the left, from the rightmost digit to the leftmost digit, we sort from the leftmost to the rightmost. The reason kind of why is if you imagine this list of items, these are all really long words. I do not want to run through the sorting algorithm over and over again because the first few digits are different. So what we're going to do is we're going to sort from the start. Now, if we just do it directly, is this going to give us the right answer? How many people say yes? How many people say no? Yeah. Can anyone explain why this is not going to give us the right answer? All right, in the interest of time, I'm going to just, yeah.
Oh, because at the end, everything is going to be sorted with everything is going to be sorted based on the rightmost digit, which, so I mean, like at the end, the ones at the end are going to be, what's it on? The ones at the start are going to be one that have the rightmost digit of A, which is not.
Yeah, like once we sort it by the next digit, we're going to end up breaking the order of the items that we really want to, right? The most significant digit should be the one that tells you which one's first. And we're not doing that anymore. But what we can do instead is we can cut the problem into smaller pieces. We cut it into individual separate subproblems according to their most significant digit, and then just run it this way. We individually sort each sub area, and we only really extend the ones that have more than one item. Because if you have only one item, it's already sorted. Now, in the best case, this means that you complete everything just by looking at the top digit. It takes theta n plus r time, but this assumes that you only have at most r items. So really, it's n less than r, assuming. In the worst case, you have to go all the way down to the end of the list. So it ends up taking Wn plus Wr time. Same thing as LSD Radix sort. Yeah. Why don't we have this problem in the LSD one? It's because we're looking at the smaller digits first, and then at the very end, we get the biggest digit. We want to sort by the biggest digit last because that gets us the final full ordering of the things.
So until then, it's just like if you have two numbers that have like 2,000 something, so like the middle digit will just sort which we go to.
Yeah. Yeah. Overall, we are going to end up getting MSD sort. In the best case, it has better runtime than LSD sort. One small issue is that MSD sort does take additional recursive subcalls, so it is going to be slower in that regard. It's going to have the same issue as heap sorting with caching. But overall, you're going to end up having this other approach to sorting things. Now, that's all I have for today. When we come back on Friday, we're going to finish off our discussion on sorting.
I have a question that's not really related, but
yeah,
if you have an existing list with like the vertices mapping to like a list of edges, is this space of that old B plus E?
Yeah.
Yeah.
Why? Can you explain what?
Because you have V keys and then you also have like a bunch of lists which all their elements add up to E. It's
yeah.
2E, I guess, if it's
2E.
undirected, but
yeah.
you take the 2 out because okay.
Yeah.
Thank you. I don't know. For some reason, I remember seeing that it was just over B, but didn't make sense.